So welcome to another seminar on the MPML, Mathematics, Physics, and Machine Learning here at IST. Today we are very happy to have with us Memming Park. So he is currently the group leader at Temporally Foundation. He leads a group on neurodynamics. And formerly he obtained his a bachelor degree in computer science in the Korean Advanced Institute for Science and Technology. Then a PhD in Florida, actually working with a Portuguese supervisor, José Príncipe, in 2010. Then after some postdoc period at the University of Austin, he moved to Stony Brook, where he became a faculty. He moved up to from assistant to associate professor, and then in 2022 he moved to Lisbon, right, to start this group at Temporally Foundation. And today he's going to talk to us about some of his work. We're happy to have him here. Memming, thanks for coming. And the floor is yours whenever you want. Feel free to start.
Thank you very much for the introduction, Mario. Let me share my screen. Okay. Here we go. So yes, today I'm going to talk about one of my PhD students, Piotr Sokul's dissertation research on asymptotic learning signals in recurrent networks. So this is a more theoretical investigation into how both biological and artificial systems can learn. And the theory is going to be presented in a way that's independent of the underlying substrate. So before I go into the details of the actual talk, a little bit of background on how we got here. So Piotr originally started studying deep neural network. When we have very deep neural network, it's typically very difficult to train those because the gradient signals don't propagate through many, many layers. Many different tricks exist in training those deep neural networks. And one of the tricks is to use specialized initialization of the weight matrices. For example, you can use these scaled random orthogonal weight matrices to initialize, and this is known to work pretty well. And what Piotr was able to do, and this was published in iClear 2020, was to understand, based on this initialization, if you look at the landscape of the loss function, using the Fisher information matrix, you can bound the curvature based on the properties of these weight matrices. So he did this theoretical study and also practical implementation of this, was able to show different convergence rates for 200 layer deep neural networks, feed-forward neural networks. And then later on with another student in the lab, Ian Jordan, who's now a postdoc in the lab, we studied now recurrent neural networks. The expressive power of recurrent neural networks is, in this case, the gated recurrent units. So if you have a simple small size GRU-RNN, the question here is, what kind of structures can it express? And what we were able to show is there are limitations as to the input-output transformation. There are certain transformations that it cannot represent in terms of a asymptotic behavior. So based on these ideas, what Piotr went on to study was slightly inspired by neuroscience questions, is to study the problem of learning in recurrent neural networks. So in particular, the question that we're trying to study here is a problem when you have arbitrary long-range temporal dependencies. So you have a brain or you have a recurrent neural network, it doesn't matter too much, and you have a task that requires this kind of temporal relation to be found in the data. So this could be supervised, it could be unsupervised, it could be reinforcement learning, any of these structures where you have input that's coming in, let's say some stimulus or input is coming in at some time point indicated by this blue thing here, and a behavior that's relevant that needs to use this information, this relevant information from arbitrary far temporal separation. So in these problems, it's not always the case in animal studies because there's always like a fixed duration that the animal has to behave, and then we can't do, arbitrary long behavioral manipulation. But in theory, there's no fundamental limit to this extent, temporal extent of this temporal separation. And many tasks, cognitive tasks, such as interval reproduction in animals and in machine learning, like copy memory tasks, these temporal separation is quite large. So the question is, how do we learn these things, and what are the problems here? And one thing to notice is that between the two time points, we need to rely on the internal representation of the system. So if you have n neurons, basically you have an n-dimensional activity vector that's encoding your sensory stimulus over time, and you need to maintain this somehow over time. And of course, there's more information coming in, and there's autonomous dynamics within the system. So all of that is bottlenecked in this n-dimensional representation over time. So one might think that if you have a good memory, right, if you have just any stimulus you have, if you can memorize this very well all the way to the future, you might be able to use that memory to be able to learn the relationship. And so this is the main question that we will try to first address. And there has been, in machine learning, and both in machine learning and neuroscience, there has been lots of attempts to understand what kind of dynamical system structure, recurrent dynamics, can exhibit this kind of long time scale behaviors, because this is very important for many, many different problems. So in linear systems, a lot of people have studied this. In nonlinear systems, people try to tune their system to have some sort of long time constant or metastable states that would maintain such a memory for a long time. So what I want to show you today is, first, I want to show you that this having a good memory and being able to learn this long temporal dependencies are not necessarily coupled together. You can decouple these two things. Then I want to tell you a little bit about how we characterize these asymptotic behavioral learning signals and why that might be a problem for general recurrent networks to learn. And then we'll show you a conjecture of sorts on the necessary condition about the dynamical system to have a good learning signal. And based on the theory that we develop, we'll provide a initialization scheme for recurrent neural networks and to show you some experiments and show you how these initialization schemes are very beneficial for training recurrent networks. And finally, I'll close by briefly mentioning some of the biological implications. Okay, so just to make sure that everybody's on the same page, a couple of mentions about learning. In general, there are two kinds of learning strategies. First kind of learning is to jump between different potential solutions to find a good solution, right? Evolutionary algorithm falls into this category, or logical reasoning, searching in the space of all possible solutions could be in this kind of category. But of course, more prominent these days is the second kind of learning, where you have directional learning signals, typically in the form of gradients, which tells you, infinitesimal direction. If you go to this direction, your errors will be decreasing. And this has been, it started really from Rosenblatt's perceptron in the 50s and Widder and Hopf's least mean squares algorithm. And it has informed all of the connectionist type analysis of how the biological brain would learn, as well as, of course, all the artificial neural networks and deep learning these days. So what is gradient? Just to make sure that we are on the same page again, I'm sure this audience is very familiar with gradient descent, but let's say you had a system where you have information coming in somewhere, you have information processing units, some neurons of sorts with some adjustable knobs. These could be synaptic weights, for example, but it could be any parameterization of your recurrent information processing system. And you have a loss function that measures how good the system is performing. And the gradient, of course, is just a partial derivative of this loss function with respect to each of these adjustable parameters. So collectively, if you have all of these gradient directions of all the parameters, you know which direction to move to if you wanted to minimize the loss function. It does not matter exactly how you minimize the loss. the theory that we will develop today is about the existence and the goodness of this gradient signal itself. And gradient-based learning is great. And mathematically speaking, if you have everything differentiable and if gradient is never zero, then it's enough to learn anything. It's pretty general in that sense. But in practice, these gradients need to be represented by something, right? In neuroscience, these gradients need to be represented by some biophysical quantity. It could be firing rate of a neuron. It could be membrane potential of a neuron. It could be some, concentration of chemicals, for example. And in digital computers, it needs to be represented by some sort of floating point representation, for example. And all of these things essentially has a limit in terms of the dynamic range. It could be a very large dynamic range, but it is limited in terms of the smallest magnitude and the largest magnitude are bounded. And with noise and numerical issues in these optimization algorithms, it is important to have, in practice, gradients that are not too small nor not too large in magnitude. Otherwise, gradient descent would suffer. And you might think this is very rare. Who cares about these very small and very large magnitude gradients? We might be we might learn very well with medium-sized gradients all the time. But this, unfortunately, is a very common problem when you get into either very, very deep architectures, when you have hundreds of layers of feed-forward system, or a recurrent network where time really is your depth of your network. And in these systems, gradient signals typically diverge or vanish. So at an exponential rate or more. So you would typically see very large or very small magnitude gradients. And this problem, it has a name. It's called the exploding and vanishing gradient problem, or EVGP for short. And EVGP is such a big problem that everybody is trying to solve this. There's many, many, many heuristics. And also in neuroscience, people have been trying to understand and tackle this EVGP problem, especially in the context of liquid state machines and chaos that are proposed mechanisms for brain dynamics. There are theoretical investigations of trying to understand this EVGP problem, but there has been some gaps. So let me just show you a little bit about the practical ways to go around this EVGP. There has been many, many, many methods. This is only a partial list here, but broadly speaking, there are some optimization tricks. You can do pre-training, you can do gradient clipping, batch normalization. These all battle against the exploding and vanishing gradients. There are special architectures, notably the ResNet or neural ODE type architectures, and also the long short-term gated recurrent systems architecture are pretty good at avoiding vanishing gradients. Also, there are special activation functions, namely ReLU and their friends, also pretty much invented for both for computational purposes, but also to avoid exploring and vanishing gradient problems. And then there are special initialization schemes or weight constraints that provide some guarantees in terms of this gradient propagation, which one of them I mentioned earlier, which is our own work. Okay, so this is all good, but these are, I would say that these are actually mostly heuristics and not based on a full theory of how exploring gradient appears. I see there's a question.
Yeah. Gonçalo, do you mind answering questions during the talk, or do you prefer them?
No, anytime is great.
Okay. Yeah, Gonçalo, please.
We can't hear you.
Gonçalo, you're muted, or we can't, or your mic is not working.
My name is Gonçalo, but I wasn't asking any question. Perhaps there's another Gonçalo in the mix.
Gonçalo Oliveira, yeah.
Oh yes. Okay.
Gonçalo, we can't hear you.
Okay, maybe type the question in and I'll try to answer as we go on. Okay, so what is the fundamental reason why we have exploding and vanishing gradient? So I will try to explain to you the fundamental reason in a easy way for recurrent neural networks. So if you have a recurrent neural network and you represent it as a continuous time dynamical system, so say you have your favorite recurrent neural network, assume that that's, with a small enough time step, it's approximating a continuous process. So we're going to focus on this continuous representation because this is easier to analyze. So let's say your X is your hidden state vector. It's evolving over time with respect to this F. This F is capturing all the nonlinear recurrent dynamics in it. The particular architectures don't matter for all the things that we're going to discuss today. So it can be a vanilla RNN, it could be a gated recurrent neural network, what have you, your special architecture. It does not matter. You have some F, and that provides you with some dynamics. And by dynamics, I'm, excuse me, I'm thinking of some sort of picture like this on the right. This is two-dimensional case. You have one hidden state on the x-axis and another on the y-axis, and each of the arrows and colors represent the direction at which this internal state is evolving over time, direction and speed by color. But once you have this kind of picture, what you can see what you can ask is this question of memory and sensitivity. So the first question, the memory question is, if let's say you had a representation of the neural state at xt0, and then we're unrolling in time this state vector at up to time xt. What does the later time xt representation say about the initial xt0 is a memory question. And the sensitivity question is, if I slightly nudge the initial condition, how does that, affect xt in later time? So this can be seen as just a simple form where you have the difference between two evolving trajectories in time. So this xt with t0 in here is the initial condition t0. How does it evolve over time with respect to this this differential equation? And if you perturb it by, let's say, a delta, big delta here, then you have two different memories. At the initial condition, they are different. How do they evolve over time? The difference, is it maintained? Can you still see that they're different after a long period of time? So that would answer your memory question. And the sensitivity is just a differential form of the same question, really, where you take the delta to be infinitely small, and this gives you this Jacobian where you have xt, the change in xt in time t, as a function of a small change in an initial condition. So this is the sensitivity. And these two things are very important, especially the sensitivity is important for us to understand learning process, because the full gradient depends on the sensitivity in certain ways. So in this equation here, the gradient, this is not the full form of the gradient, but this is the major contribution of the full gradient respect to wi. You can see that it's integrated over time from t0 to t1. This is let's say a finite interval. And anytime you need to relate the changes at time t to the time t1, where the loss function here is evaluated type t1 only, it's linked through this Jacobian matrix, this future past Jacobian matrix, which is exactly the same form as the sensitivity, is just an inverse reciprocal of the sensitivity called the adjoint. And this is analogous to the backpropagating gradient, the term that you multiply W transpose repeatedly if in a standard neural network architecture. And so this guy, as time between t0 and t1 gets longer and longer, this guy is the one that's stretching and contributing to exploding and vanishing gradient problems. So let me illustrate this in a very simple case. Let's say you had the full state space here. This is just a two-dimensional illustration, and this red dot here is a global point attractor, meaning anywhere you initialize the network eventually gets to this red point. And if, let's say you started at x0 here with a delta, you have two different initial conditions, they will eventually get near this global fixed point, point attractor, meaning any change, any difference between the two, this memory bit will decay. At infinite time, they will go to 0. So everything is forgotten, and asymptotically speaking. And also the derivative, the sensitivity, will also be diminished. So this is the vanishing gradient case. So you might think, the vanishing gradient and memory are very tightly related, but there is a case that they are not related. And this is one example, the simple example where you have two bases of attraction. If you initialize your state in the left basin, it will converge to this left point attractor. And if you're on the right side, you go to the right one. So in this case, small changes, the sensitivity still vanishes to 0. If you start on the left or the right, they will all both vanish. So the learning signal will be, you'll have vanishing gradient. But the identity of where you started, if it started on the left side or the right side, that basin of attraction, is not forgotten. So you get one bit of information through this process. So you have very good memory. It's even robust to small noise perturbations. And this memory is forever, but you don't have any learning signals. So if you wanted to learn small perturbations, relationship between the past and the future in very long time scale, it's not going to learn very well if your neural network is currently exhibiting this behavior, this bistable behavior. And this is not new. This was known, reported in 1994, Yasha Benja's paper, where they wanted to have this 3 criteria they wanted the recurrent networks to have. They wanted to have infinitely long memory. They wanted to have robust memory content, robust to small noise perturbations, and also have no vanishing nor exploding gradient. And what they concluded is that since you really want to have the first 2, you cannot have the third one. Because once you have attractor dynamics with a bunch of point attractors, you will definitely have vanishing gradients. So they said, oh, okay, we can't avoid having vanishing gradients. But this is not the full story. So our theory continues from here. And we are looking for something that's non-vanishing and non-exploding gradient. So what we're trying to find is what are the dynamical systems that would give you the non-vanishing and non-exploding gradients, and can we utilize them in a way that has not been before? So to do this, we're going to use this quantity called the Lyapunov exponent. This is a scalar quantity per dimension that tells you if you perturb the system in that particular dimension, what's the rate of either divergence or convergence. So it's basically an exponential time constant measured in a asymptotic fashion. So if you have this x0 state, you perturb it a little bit, and if this difference increases in this exponential way, then this lambda is approximately the Lyapunov exponent. The exact definition is in the bottom here, where it depends on where you started, the initial condition, and the direction at which you perturbed it. And the main quantity here is the normal of the Jacobian here in that direction, how that evolves over time in the limit of t goes to infinity. So this really is an asymptotic quantity. It doesn't care, transient amplification and whatnot. So since there are many, so if you have an n-dimensional system, you have n number of Lyapunov exponents for each initial condition. But if it's a generally an attractor system, for each Bayesian attraction, everybody in that same Bayesian attraction gets to the same final attractor. So actually, they will share the Lyapunov exponent or the Lyapunov spectrum. So you have n number of numbers basically for each system that we want to study. It could be positive, which means the corresponding gradient in that direction will be exploding. It could be negative, which means it's vanishing. It could be 0, which means it's sub-exponential behavior. It could be just marginally stable and not move very much, or it could be sub-exponentially changing over time. So just to basically illustrate the 0 Lyapunov exponent case, if you look at the right-hand side, there's this red line that I drew here. This is the line of 0 flow. So outside of here, you get attracted to the line, and on the line, you're just staying constantly over there. So these two x here are two different initial conditions. They will never move. Once they're on it, they just stay there. There's one dimension, that dimension that's corresponding to this line, that has zero Lyapunov exponent, and the other dimension is in this two-dimensional cartoon. You have one negative Lyapunov exponent. So one vanishing gradient and one non-vanishing, non-exploding gradient dimension. So this third kind of system is called a continuous attractor dynamical system. So basically, you have no flow within that low-dimensional manifold, and it's attracted to this manifold. And this has been widely used to explain how the brain, the biological brain, remember things. So in this particular paper, the experiment was pretty simple. The monkey has to remember some value, in this case, by color-coded, 10 hertz to 34 hertz. It doesn't matter too much what this was, but at the time of the yellow bar, the monkey was given the stimulus, and the stimulus is gone. So, and the monkey has to wait a couple of seconds or so, and report based on what the input was later on, to compare and report what that report number is. And if you record from a prefrontal cortical neuron, sometimes you'll find these neurons that encode the different inputs at different activity level. These are firing rates of a single neuron, average across multiple trials. And you can see that if the stimulus was 34 hertz, it maintains this high firing rate during the delay period. So there's some persistent activity, or this ongoing activity, that seems to be maintained more or less in a constant fashion over time. And so this was this was taken as an evidence to support the hypothesis that the way that memory is encoded is, first, in the encoding stage, you would put, this is the x-axis here is the neural activity, you would change the dynamical system such that you would encode the input, put the state into one of these ball, the red or green or blue ball locations. And then during the maintenance periods or the memory period, you will have a flat dynamics, meaning there's no flow. If you're at the blue point, you just stay at the blue point during this whole time, and then later you use that information. So in general, it doesn't have to be one-dimensional. It could be high-dimensional attractor. It doesn't have to be a line or a plane. It could be a curved manifold. It could be any shape of manifold to be a continuous attractor. But there's one major problem of using continuous attractors as a system for memory and for learning, which is the fine-tuning problem. Basically, the fine-tuning problem says if you perturb the dynamical system or the parameters of the recurrent neural network or some synaptic connectivity just a tiny bit, this zero Lyapunov exponent plane or the manifold will just disappear suddenly. And it has to be very, very precisely tuned. So for example, this very simplified linear recurrent neural network where the neuron, each neuron xi, forgets with a time constant tau, so because minus xi here, so it forgets itself, but you can try to tune the recurrent connection through the whole network of xj's such that the combined effect exactly cancels out this forgetting factor. So your recurrent connection has to match this time constant to make it exactly constant, right? So this -1 here will be canceled by +1 eigenvalue here, basically. And this is a very, very, very fine-tuned set of parameters. Any change in Wij will destroy this. So there's a second class of networks or dynamical system structures that exhibit a zero Lyapunov exponent, and this is the stable limit cycle dynamics. We have found this back in 2019 in a short report. And what we found is that if you have, let's say, again, a two-dimensional cartoon of the system, if you have a limit cycle, meaning the activity is spontaneously oscillating, and it's a stable limit cycle, meaning if you perturb it a little bit away from this limit cycle, you come back to that limit cycle. So it's a nonlinear oscillator. And in this case, if you perturb it in the direction of the phase, if you push forward the phase a little bit or pull the phase backwards a little bit, that change in phase, depicted here as delta infinity, will be maintained forever. Right? It doesn't go away, just like the continuous attractor. But this one is not constant in time, it's constantly oscillating in time. So infinitesimal perturbations on the phase is not forgotten, which means sensitivity is not zero, nor it's neither vanishing nor exploding over time. So it has good learning signals. And we know the exact solution for this. If you linearize such a system, we know the sensitivity will be periodic. And that one dimension represents one dimension of non-vanishing, non-exploding gradient, exactly one zero-Lyapunov exponent. Here's a quick illustration of how this looks. The black line here is the ongoing activity of the network. So the recurrent neural network is two-dimensional recurrent neural network. It's oscillating in time. And if you try to do backpropagation through time, the backpropagation signal itself is this orange guy. This is the adjoint. And you can see that it's oscillating, it's periodic, not exactly the same shape. And it's more of a shape of the derivative of the original signal. And it goes forever. So this signal can connect between two arbitrary time points. And you can have more than one of these. So if you have multiple of these stable limit cycles, let's say they are independent, then they could form a quasi-periodic attractor, especially when their frequencies of oscillations for each of these independent stable limit cycles are not rational multiples of each other. It'll fill up this entire torus. So it's hard to depict, high-dimensional torus here, but you can think of it the two periodic boundaries as being each of these phase variables. And if it's in this condition where the periods are not rational multiples of each other, it'll be quasi-periodic, as in it'll never repeat itself, and it'll fill up the whole torus. Well, densely, it'll pack the torus over time. And importantly, these stable limit cycles do not suffer from fine-tuning problems. So there's in the parameter space, there's a huge chunk of parameters where you perturb the system a little bit in any direction, you would most likely just have slightly different nonlinear oscillator. You could get away from it, of course, if you change the parameters a lot, but you don't have the fine-tuning problem. So while learning, when you're taking some gradient steps, you're changing the parameters. This property of having non-vanishing, non-exploding gradients will not disappear as quickly as the continuous attractor case. So to summarize these two types of dynamical systems, we have the continuous attractor. If you have a d-dimensional manifold where you have this arbitrary manifold of, let's say, a d-dimensional hyperplane, then you have d number of zero-Lyapunov exponents, which can carry d different directions of gradients that will be maintained over infinite time. But this is fragile. As soon as you take a couple of gradient steps to learn, the continuous attractor disappears. And the second case, where you have periodic or quasi-periodic attractor case, then you have a d-dimensional torus, and you will have d number of zero-Lyapunov exponents. Your learning signals will be periodic or quasi-periodic, and now you're robust to perturbation and primers. So the structure of propagating learning signals over a long time will survive much longer. So our brief conjecture is that these are the only cases that this stable limit cycle or the quasi-periodic toroidal attractor case are the only robust case where you can carry the sensitivity information for a very long period of time. That's our main conjecture. So now that we have some theory, let's look at some applications. So what we're going to do is we're going to find parameters for a particular parameterized RNNs that exhibit stable limit cycle. We will initialize the RNNs in this regime and train on difficult tasks, and then we'll see if it's good or not. So we're going to consider vanilla hyperbolic tangent RNNs and the gated recurrent unit RNNs for this experiment. And we do so because for these systems, we know exactly when oscillations appear. So this was one of our previous studies where we were studying the expressive power of gated recurrent units, where we found there's a particular set of parameters that would generate through this hop bifurcation limit cycles more sinusoid looking, all the way to very, very nonlinear looking oscillations here. So this is the basic parameterization of our network. So x dot, or in continuous time, or xt plus 1 minus xt in the discrete time RNN case, we're going to have a 2x2. This is a two-dimensional case. We're going to have a rotation matrix as our weight that connects from past to future. So we have a parameter theta that selects how quickly it's rotating, and alpha that is the magnitude of of this matrix, and then it's going to go through some nonlinearity. So if you choose this particular parameterization of alpha and theta and look at the largest Lyapunov exponent, so that's the color here. So x-axis here is the theta axis, y-axis is alpha, and white color here corresponds to the zero Lyapunov exponent. So there's a huge region in the parameter space that you can see that the system is oscillating, which is shown here by the power of oscillation on the right-hand side. And they have exactly 1 zero Lyapunov exponent in the continuous case. And in the discrete case, it looks slightly different, but there's also, there is this region of parameter space that we know that contains these stable limit cycle. So what we're going to do is we're going to draw random samples from this parameter space to create a bunch of random oscillators, 2 by 2. So each pair of neurons will contain these oscillators, and we're going to generate a bunch of independent oscillators. So our full recurrent neural network will be a 2 by 2 block matrix, where each block has this random 2 by 2 rotation matrices. And we're gonna use this because this gives us a toroidal attractor type system, and we know that this system will have at least n/2 number of dimensions where we can carry gradient signals, learning signals over time. Okay, any questions about this formulation? Okay, so the experiments, I'll show you a few of these experiments. We're going to compare multiple different things. The first experiment was the copy memory task. So this is just a sequence of discrete symbols every time point, and you have to use the first few symbols and spit it out later. So it's a memory kind of task, but you need to learn which one to memorize and which ones to ignore. This is the learning performance graph, the test loss on the y-axis, training epochs on the x-axis. We're comparing tanh with the limit cycle initialization, which is a small symbol here, versus random initialization and orthogonal initialization. GRU with the limit cycle initialization, random GRU, and LSTM, where the forgetting gate was tuned to close to very long-term memory. So among these methods, really only the limit cycle initialization cases could learn this very quickly and reliably. No other tricks, no crazy tricks. It learns this extremely long temporal dependence problem pretty well. Here is the random delay version. The copy memory can be a fixed duration, so just 2000 time points, and then you have to spit out whatever you solved at the beginning. And the random delay version is there's given a queue. Whenever your queue is given later on, you have to spit out whatever is in your memory, and you have to choose what to memorize. And only the GRU with the limit cycle initialization could find a good solution for this particular problem. Right, so this is comparing our competing method, co-RNN, which is also based on like orthogonal or rotational kind of dynamics. And we're doing pretty well in both in permuted MNIST, which is one of the standard, not so physiologically relevant tasks, and sequential CIFAR test. This is higher is better in this case. Both GRU, again, GRU and GRUs were better. And in this case, the tanh with the limit cycle initialization was the best in this case. Okay, so, and one thing to mention is that sometimes, so the main thing is that where we initialize the network is letting us reach solutions that could not be reached from other initial conditions, right? The other initialization has limits of just, what kind of solution they can reach. What we're really allowing here using this limit cycle initialization is allowing us to get to these solutions that were not easy to get to with previous methods. And the oscillations don't have to always be there for permuted MNIST. I think it was still there at the end for the random delay copy memory task. At the end of learning, there was no longer limit cycles anymore. So you use the limit cycles to get to a solution, but once you get to a solution, you don't need to be oscillating because the solution does not require you to oscillate. It's not helping you. So the final GRU solutions here had no sign of oscillations. Okay, so those were the numerical experiments. I'll just say a few words about the biological implications here. So what we think we found is a necessary condition for having these, allowing gradient-based learning to learn long temporal dependence, but we don't know how this could be implemented in a biological system yet. But we have some ideas of what we might see if that's the case. So what we expect to see from the brain is that we will see oscillations at rest when there's no active task going on, or maybe even within the active task. And these oscillations will be at multiple frequency, not completely synchronous all the time, because then your dimensionality of your zero Lyapunov exponent will collapse. This is and this is indeed what we see in EEG spectrum, for example. If you look at the POW spectrum of EEG, you would see broad oscillatory bands with a huge amount of oscillation, especially at rest. We would expect the learning signal or the eligibility trace, if it's a reinforcement learning type method task, then these signals would be quasi-periodic. Of course, it's hard to check that it would be quasi-periodic, and in measurements, we don't know exactly what to measure to find this out, because there are many different hypotheses of how eligibility traces are implemented. But one thing is that if we can find out that in the absence of oscillations, long temporal relation becomes more difficult to learn. Maybe opportunistically we can find out, oscillation power sometimes goes down temporarily, and in those periods it's harder to learn. Or if we can reset the phases of the oscillators by some sort of external stimulus, this should also disrupt learning, right? It may not disrupt the exact representation in terms of spikes per se, but the oscillations we see might be disrupted separately. And if you can do so, we might be able to disrupt learning only the long temporal relations. So that would be an exciting prediction to make. Another thing is that the inputs to the system should have desynchronizing effect, and this could last for a longer period of time if it indeed is for learning long periods of long temporal dependencies. And finally, if this theory doesn't only require this continuous variable in a continuous state space, even within a single neuron, if you think of a single neuron, there are neurons that are just pure oscillators which fire action potentials in a periodic manner. And those neurons that fire action potentials in a periodic manner really contains within it this quasi-periodic activity. And the phase of that periodic oscillator on its own has the same property as what we described today. So if you have a neuron that has baseline quasi-periodic firing pattern, this may be a neuron that's involved in learning long temporal dependencies. The main issue of all of this, though, is a big one, is that all of the experiments we did and all the theories that we were trying to derive are more machine learning based, where we can actually do backpropagation through time, which means we can go back in time, find out what the activity was, and change the synaptic weights, which is not a causal process. So if you want to learn in a causal manner, it just you see one example at a time. Time only flows forward. You somehow need to propagate the sensitivity forward in time and not backward, which is not necessarily easy to implement. And we have not yet found a very nice way to do this in a general format. But we're excited to expand on this particular direction. Okay, with that, I will quickly summarize. So the theory that we developed only depends on the topology of the dynamical system of your RNN. Does not matter what exactly the architecture of your RNN is. It matters what effective dynamics it implements. And that's what is important for understanding the corresponding EVGP problem or avoiding the EVGP. Non-vanishing and non-exploding gradients can be achieved in a non-trivial system, and the robust solution, we think, is only achievable with stable limit cycles or quasi-periodic attractors. And using this stable limit cycle initialization is very effective in solving long temporal memory tasks with RNNs. All right, well, with that, I would like to thank my lab. This was a tremendous amount of work by Peter with help from Ian and Evan. And special thanks to Dong-Sung Ben-ha, who has really started this line of research in my lab. We just had one conversation at a conference, and this started a cascade of research ideas, and of course the funding sources. Thank you very much for your attention.
Thank you very much, Memming. Thank you very much. So there's some applause going on. So are there any questions for Memming? Just raise your hand or unmute yourself if you have questions. I have a question myself while other people think about questions. So this is very interesting, of course. So I have a question in maybe that I did not fully understand your slide 34, the one where you had these comments when you mentioned these spiking neurons. Well, these neurons that you mentioned, they oscillate autonomously. Is that the case?
Right. Yeah. There are some neurons that oscillate.
The dynamical systems that you consider are, once learning is done, they are time invariant dynamical systems, right? At least in theory.
Yeah, I mean, after they learn, they may still oscillate. They
oscillate. They are dynamical systems, but your function f is always the same, stays put, right?
Right. I mean, autonomous as in input, not input driven.
No, I didn't mean autonomous, homogeneous, time invariant.
Yes, these are time invariant.
Time invariant. But it's known that one way to make a system stable is to make it slightly time variant. If some parameters oscillate, for example, that will widen the basins of attraction, for example. Is that some strategy that somehow the brain uses, and maybe that's why you have these autonomously oscillating neurons going around?
I see. So a control theoretic perspective.
Yeah.
Injecting...
So one very famous example is if you have an inverted pendulum, it's unstable, right? But if instead of having it, the axis of the pendulum being fixed, you have it oscillating, that makes the inverted pendulum stable. It gives it a non-zero basin of attraction.
Right.
Of course, but the oscillation is completely independent of any input to the system. It's just the system is no longer time invariant. It is oscillating at some frequency. The parameters of the system are oscillating. Do you think that this could be some strategy that the brain itself uses to gain some sort of stability in its attractors?
I mean, honestly, I do not know, because it's an interesting perspective, but I don't think it's a widely considered perspective. There are many stable states anyways. It's not like it's the brain's problem is not to create new stable states. I mean, that could be a problem, but it could be achieved by different ways. What I'm trying to convey here is that having stable states is bad for learning.
Too stable. Okay.
Because once you have stable states, it correspondingly has a vanishing gradient.
Mm-hmm.
So
Yes. Yeah.
yeah. But for memory or other control tasks, or if maybe generating stable output, such oscillation stabilized systems could play a role. Yeah, but I don't know if it's such an example.
Okay. Any question for Memming? I had another question on slide 21. I don't remember what it is, but I wrote down 21. Can you go to slide 21? Please.
And try.
Yeah, so in this fine-tuning problem, are you somehow assuming that in these Wij's, that Wii, so the diagonal is the one that is being responsible for canceling the decay, or is it the whole thing together that is responsible for canceling the decay?
There are many solutions. In this case, I'm assuming there's no self-connection, but even with self-connection, it is still, there's this fine-tuning problem exists. So you could try to do this with one neuron, and it will still have a fine-tuning problem. But as a network, typically this is written out as a network because the continuous attractor is presumably a robust quantity, the object that's implemented by a huge number of neurons together. That's why I wrote it in this form. It doesn't matter too much exactly the form of this recurrence. The problem of fine-tuning is regardless of your parameterization of the recurrent dynamics, the zero Lyapunov exponent solution to generate that's results from a x dot equals 0, right? Basically having zero flow is very sensitive to any perturbation in the parameters.
Okay, yeah, that makes sense. Okay, any question?
I have one, and
please.
I didn't get, there were a few things that I didn't get, but so I'll ask out of sheer ignorance. Are these behaviors specific to the fact that you're then exploring the space through stochastic gradient and an approach like like gradient descent, and if you use something like stochastic gradient descent, and some of these effects wouldn't be there, and so, but because you want to see these very specific effects, you sort of can't use stochastic gradient descent because the noise would create some kind of extra regularization or anything like this. Does my question make sense? Or perhaps I'll put it like this: is there a difference between, is this behaviors that you're positing here, are they specific to gradient descent, and would you expect to see something different if you use stochastic gradient descent to explore the space instead?
It applies to any gradient-based learning. So it could be ADAM, it could be gradient descent, it could be accelerated gradient descent, it could be stochastic gradient descent, it could be batch. Anytime you rely on gradients to learn over time, right? When you have this backpropagating gradient that you need to rely on, this problem exists. The exploding and vanishing gradient problem exists. And what we observe on the experiment side, when we did all these numerical experiments, of course we used a particular stochastic gradient algorithm. I believe this was mostly ADAM that we used to train. Is that right, Piotr? Yeah, Piotr's nodding his head. These were a particular algorithm, but this result does not depend on which algorithm you use. It's a universal fact, basically.
Okay, thank you.
I might add that it also holds for second order optimizers. So it is really like a very general phenomenon. And it is just the inherent property of the dynamics themselves that dictated the dynamics given a particular set of parameters, and how you explore the parameters is somewhat less important.
Okay.
Thank you.